Okay, we're going to work on the Inertial Balance Inquiry. So if you're on the website, click on Math Foundations, and we'll click on the Inquiry Inertial Balance. And that'll take us to the inquiry, and we have several inquiry questions that we're going to try to run down through here. And the first thing we're going to look at is what is an inertial balance? Inertial balance is basically a tray that's on a spring, and I can pull it back and then let it oscillate back and forth. And I can put different masses on there and measure the period of oscillation. So the period is how long it takes for the pan to go back and forth once. It's a period of time in seconds. And the more mass you put on there, the period will change. So what we're interested in looking at is what's the relationship between the amount of mass and the period of the pan. So we're going to go ahead and do this experiment, and then afterwards we will look at our data and try to analyze the relationship between mass and period. Okay, we're going to do the inertial balance inquiry. We have an inertial balance here, and we can use this to determine the mass of an object. It's not based on gravity at all. It's based on the elasticity constant of some spring. So I can pull this back and I can let it go, and it's going to go back and forth inside this photogate. The photogate's hooked up to a computer, and I'll let it go for a little bit, and then I'll stop it, and then it'll measure the period of time, which basically is the time it takes for the thing to go through once and back to the same spot. So we'll get all the periods of time, and what we'll do is we'll continue to add more masses on here. We're going to add 20 grams on at a time, up to about 300 grams, and then we'll see how the mass then affects the period. So our mass is going to be our independent variable, and the period then will be our dependent variable, and will depend on how much mass we're putting on there. And then we'll be able to graph and try to figure out the exact relationship between mass and period. So we'll start this, and we'll measure the period of, we'll keep adding 20 grams, we'll measure the period every time. So I'll let it go, and then we'll stop it, and that'll be good enough. And we'll loosen it up a little bit, put on another 20 grams, and we'll let it go again. And that'll be good. And we'll write down the time periods. I'll give you all the periods here in a little bit as soon as we're done with the experiment. And we'll keep on continuing on. And we'll speed the video up. Okay, we're now at up to 200 grams, and you'll notice that it goes a lot slower the more mass you put on, so that's a general relationship. We want to figure out the mathematical relationship later. We'll do 100 more grams. And finally, we'll put the 300 grams on there now. Tighten it up, let it go. And you'll see it's going pretty slow now. Okay, so we get all those periods of those. One thing we want to do before we end this experiment, we're going to put an unknown mass on here. Later we're going to have a graph, and so we're going to be able to use that graph to predict what masses will be based on certain periods. So I'm going to take all these masses off of here, and I'm going to take an unknown mass, this wheel, and I'm going to put it on here instead. Okay, and we will let that one go, and we're going to get the period of this wheel. I'll record that later in the rest of the video later, and we'll be able to use that to predict what the mass of this wheel is. I'm going to go put the mass on the scale as well, and so I'll be able to tell you what it is after we try to predict what it is. Okay, after you've done the experiment, we're going to come onto here, and you're going to click on this Google Sheet template, and that's going to bring up a template I've already kind of made for you, and you'll be able to answer your questions. So the first thing you want to do with this template is go up to File and make a copy, wherever that is, right there, make a copy. And you can say inertial balance. You can type in your name. Okay, click OK. make your own copy of it. All right, so if we look on the thing, on the website, we're going to go down these inquiry questions. And number 1 says, determine the mathematical relationship between period and mass for the classroom balance. We want to figure out what's the relationship between those. So, so in the experiment, we measured the period of a whole bunch of masses, 20 grams up to 300 grams, and we have the periods recorded right here in this template. Up here, we also put on the little training wheel on there, and we got the period of the wheel. We'll use that a little bit later. So the first thing we want to do is we want to put in the masses. I didn't actually put the masses in here for you because I want to show you some things with Google Sheets. So over here where it says mass in grams, we're going to put in 20. And then we'll hit return, and we'll put in 40 and hit return. And that's all we really need to do, because if you come up here and click on the 20 and hold down Shift and click on the 40 also, and then grab on the little dot there on the end and pull it down, Google's smart enough to know that you're going to try to implement it, increment it by 20. So it goes all the way down to 300 grams, which is what we did. Now we actually want to convert, we want to MKS unit this. We want these masses to be in kilograms. So we're going to do that in this next column here. And the way we can do that, we can let Google figure it out for ourselves. So we can do equals. We can do a formula. We can do equals. And then we can grab this cell, click that cell. And how do you convert from grams to kilograms? Well, you're going to divide by 1,000. So I do equals, and then that cell, and then I do a slash, and then I do 1,000. Hit return. And there it's converted to kilograms. I don't have to do that for every single one of these. I can just click on that cell. I can grab the little corner and drag it down. It'll actually copy that cell all the way down. And if I click on like something down here, you'll see that it actually incremented that cell. So it takes B13 and divides by 1,000. So that's really nice that it increments it for us. So here's all of our masses. Okay, so I want to graph. I want to make a graph of mass versus period and see what kind of a relationship was there. So I'm going to get a graph, and then I'm going to analyze that graph and see kind of which one of the 7 graphs that you have in your notebook is it similar to, and try to figure that out. So mass is going to be my dependent variable. So I put on different masses, and then I saw what happened to the period. So the period is our dependent variable, and the dependent variable usually goes on the y-axis, and dependent variable goes on the y-axis. The independent variable, which is our mass, goes on the x-axis. So your y depends on your x. It's like a y is a function of x. So we always put the dependent on the y and the independent on the x. And if you want to do this right in Google, you always need to have your x column first and then your y column next, because we're going to highlight this data and graph it, and it's going to assume that you know what a normal XY table looks like. The x comes first and the y comes second. So I'm going to highlight all of this, and I'm going to come up to insert, and I'm going to do a chart. And here it is. And it's going to put in this line chart, which is okay for us. And so I have this kind of a graph, this shape graph. And you'll notice right away that it's not a line. It's not a straight line. Which one of the 7 graphs does it look like? And so I think if we look at the iPad here real quick, it's like one of these graphs like this, kind of looks like that. And this is the y. And down here is the x, and this graph is not a straight line, so it's not like a y equals mx type of a graph. It's curving down here towards this. So this is, if you look at your graphs, by the way, proportional, I should say proportional. So y is proportional to the square root of x. That's the way that this relationship actually is, or it's what it looks like. We're going to try to prove that that's actually the relationship. So that would mean that the period is proportional to the square root of the mass. It's not just proportional to the mass, it's proportional to the square root of the mass. Now, another way I could write this is, because we don't like radicals sometimes, I could square both sides, and it looks like this graph is saying that period squared is proportional to mass. That's what it looks like. And so we want to prove that that is actually, that's actually the relationship. Okay, so we'll go back here. And just to prove that this is not a straight line, what we want to do is we'll come into, well, let's look here. We got some things we need to change here. It says it tried to do a title, wheel versus inquiry balance name. I don't know why it did that. let's go to customize, go to chart style. And a chart style, there's some things you can do. Background color, I can make a different, I can make like a little blue background. Border color, I can make it, I don't know, green, I don't know, whatever, black. Okay, close chart. Go to chart and axis titles. That's what we want. Chart the title. Okay, so we're doing period versus mass. Period versus mass. Okay, and let's see. Okay, we had some things that are kind of messed up on this. So chart and axis title. That's chart title. Horizontal axis title should have been the mass in kilograms. And the vertical axis title should have been the period in seconds. Now yours might have come out right. It could have come out right. So you might have to change these things, but that is how you change them. Okay. So we want to come down to the series, and this is line 1. This is the first thing we have here. And we want to come down here to the bottom, and we want to put a trend line through this. A trend line is always valuable to see how linear is it, because our whole goal will be to make this thing linear. So I put a trend line through it, and you'll see that it's clearly off the line. It comes up over the line, it's off the line here, and then it comes down below the line again. It's clearly curved. And we want to see how linear is that. So I show an R-squared value right down here below. I show an R-squared value, and it's 0.974. Remember, a line would be 1. An R-squared value would be 1. So it's, it's not too far off, but it's in terms of graphs, this is actually fairly far off. Okay, so it's definitely not linear. Okay, so what are we going to do? All right, well, we think this graph looks like to us that it's a y proportional to the square root of x, or it's y squared proportional to x. Either way is the same thing. So what we're going to do is, and since we don't like square roots, we're going to modify the y-axis. So instead of graphing this x versus this y, we're going to graph the mass versus what we think the relationship actually is. We're going to graph it versus period squared. Period squared. Make that look nice. I'll center it and bold it. Okay, period squared. So I'm going to square this entire column, and then I'm going to regraph mass versus the period squared to see if that indeed was the relationship. Because if it is the relationship, it'll actually be a linear line. It'll be a linear line. We graph the two variables at first to see if we recognize the graph, and if we think we do, then we graph what we think that relationship was, and it should be linear. So I'm going to take equals. I'm going to do equals. I'm going to click this. I'm going to do square root, or I mean the square of it, sorry, a caret 2. I'm going to square that. And I'm going to take that equation, and I'm going to drag it all the way down. Okay? And then I'm going to graph mass versus period squared. Here's the moment of truth. Now, actually, what I'm going to do is I'm going to graph it on the exact same graph. So I'm going to double click on the graph. And let's go down to series. Actually, no, I can't do that. I got to go to setup. And you'll see that the data range was C6 down to D20. So that's right here, C6 down to D20. So that's just that data range right there. So, whoops, I clicked off it. Okay, so what I want to do is I want to go from C6 down to E20. So I'm going to change this. Whoops, right here, data range. I'm going to click on that. And I'm going to come in here and say I want to include column E too, E20. Click OK. That doesn't change anything because your x-axis is still C6 to C20, which is your mass, and your first series was D6 to D20, which was the period. But now I want to do is I want to click on add a series, and you'll notice now there's another one available, E6 to E20. I could put that as a second series, and I'm going to do that. And it graphed mass versus period squared right here. Okay, so what I want to do on that is I'm going to go to customize. I'm going to go to series, and let's see, we have apply to all series. Okay, so I want to come down here and I'm going to click on line 2, the red one, and come down and put a trend line through it. Okay, now I did that, and you might notice that you can't hardly even see it because it's like right on it. So this is going to be really, really linear. In fact, let's see how linear it is. Click the show R squared value. And I'll close this for a second. And look at R squared is 1. It's like perfectly linear now when I graphed masses versus period squared, which that proves that is definitely the relationship. Somewhere in this physics equation, you have mass on one side and you have period squared on the other. Now, there's a whole bunch of other numbers and constants in there probably, but that's how these two variables are related in the physics equation, mass versus period squared. I haven't showed you that physics equation yet. We'll look at it here soon, and you'll see that, yes, you figured out what the relationship between those two variables are. All right, double click on this again because we need one more thing. Go to Customize, go to Series, click your line 2, and in this one, we actually want the equation. We want the equation. So, and where it says label, this is hidden really well. Under where it says label, it says custom. Click on that and click use equation. So if I close it, it's actually going to put an equation on here. It's like an mx plus b equation. You'll notice that your y-intercept, the r squared one is over here. Don't confuse that with the equation. So here's your equation. Y equals, and then you have 0.395x, and remember x is your mass. And what is your y? Your y is actually period squared for this one. Your y is t squared. So t squared equals this x or m plus, and here's your y-intercept, but look at your y-intercept. It's negative 17. So what are we going to do with that? We're going to ignore it. We're going to just pretend it's like 0. Okay? All right. So if I look on the iPad, I'm going to write that equation. It's going to actually be t squared equals 0.395x, which is m, the mass, plus basically 0 y-intercept. So I'm just going to use this as my equation for this inertial balance. It's a straight line equation, right? Y equals mx. That's why it's a straight line. But my y is t squared we showed. Okay, so I'm going to use that equation, okay, in the rest of this lab. Okay, so that's part 1. Very good. We've figured out, oh, by the way, make sure you put your name up here, okay? Because you're going to print this off and insert into your notebook. Okay, we're going to go on to part 2. And part 2 on the inquiry, if you go back and read it, it says write a little program that says if you enter the period, if like you put some unknown mass on our inertial balance that we have at the school, and you get a certain period, what will the mass be? So you'd write a computer program so that they hook it up to the mass, so it measures the period and it just spits out what the mass is. So that's what I want to do right here. I want to enter in some kind of a period here, like the period of the wheel. Okay, I'm going to put that period of the wheel in there, and I want it to automatically just tell me what the mass is right here. So how would I write this program? Well, right in here, I'm going to write the equation to how to solve the mass. How do I do that? Well, let's go back to the iPad. What do we have? We have t squared equals 0.395 m. So how do I solve that for m? Well, m would equal t squared over 0.395. So all I got to do is take the period, square it, divide it by 0.395, and that should be my mass. Now that'll be your mass in kilograms, right? In kilograms, and we actually want this mass to print out in grams. So if this is in kilograms, what do I do? 1 kilogram is 1,000 grams. So I'm going to multiply this equation here by 1,000. So I'm going to take period squared times 1,000, divide by 0.395, and that should be my mass. So that's how I'm going to write this little program. So down here where it says mass, I'm going to do equals, and I'm going to take the period that's going to be entered into the program right here. So I'm going to click that cell. That's the period they're going to enter, and we're going to square it. So square it. And we're going to take it times, which is an asterisk, times 1,000. 1,000. And then we're going to divide it by 0.395. And that should be our mass. Okay? All right. 2, 3, or something like that. Okay? And it's good. So I can put the wheel in here. I'll copy the wheel. Let's put it in there. Okay? And hit return. And I get a mass of 142 grams. Okay? or about close. Okay, now that actually is really good because I did put the wheel on the scale and it was 142 grams. Okay, so that works out very, very nice. All right. Okay. So that's good. So there's our little program. I could put any kind of thing in there. What if I had a period of like half a second? If the inertial balance has a period of half a second, the mass is actually 632 grams. Okay. So there's a little computer program that I use for the equation that's going to tell me if I put a period in, it's going to automatically calculate the grams for me. Okay. That's excellent. All right, let's look at number 3. It says, if the equation for the period of an inertial balance is actually given as the following, where m is the mass and t is the period, calculate a numerical value for k, which is the spring elasticity constant for our balance. Just ignore the y-intercept value in your equation. All right, what does this mean? This means that this is the actual equation. This is the relationship between period and mass. And you'll notice that here's a period on the left side, and over on the right side, you have a square root of a mass, which is what the relationship was that we proved. I could square both sides and have a t squared on this side and an m on this side. That's exactly what we proved was the actual relationship. So if let's find the iPad again. Let's find the iPad. Okay. So if I had t squared, let's see, I had t squared equals, what was it? It was 0.395 times the mass. That's the equation we figured out from our graph. Now, what they're telling us is the actual physics equation is T equals 2 pi times the square root of m over k, and k is an elastic constant for the spring. All right, this part gets confusing to people, so I'm going to show it what we're doing. So we figured out, all we were trying to do is figure out what's the relationship between period and mass. We figured out that it was period squared is proportional to mass, and it's actually proportional to mass with this constant 0.395. We figured that out. Hopefully you understood that part. Now what I'm telling you is here's actually the physics equation. This is the physics equation, which is great because it shows the relationship is the same. Whoops, sorry, that's not period squared. That's period is proportional to 2 pi times the square root of m over k. Okay, now what I want it to do is I want it to kind of look like this. So I want to square the period on this side. So I'm going to square the period on the other side, and that means I have to square the entire right side also. So it'd be 4 pi squared m over k. Okay, so this is the physics equation. Okay, this is the equation that we figured out for our inertial balance, the relationship between period squared and m. So what they're asking is for us in this problem 3 is, can you now figure out what the k value is for our inertial balance? Can you figure out what this elastic constant is? And we can, because if you look at this equation, okay, and I'll kind of change colors here. If you look at this equation here, you have kind of a slope of the line, 0.395. Well, in this physics equation, that has to equal the slope of this line, right? So I have t squared equals this number times m. Here I have t squared equals this number times m. So these two have to be equal to each other. So I can do 0.395 equals 4 pi squared over k. So k would equal 4 pi squared over 0.395, and I can actually calculate then what is the k value, the elastic constant of our inertial balance. So I'm going to let the Google do that for us. So down here in part 3, what's the spring elasticity constant of k? So I'm going to type in here, I'm going to do equals 4 times asterisk, and I'm going to do pi. You can do 3.14, but there's actually a built-in thing. I can do pi. And you actually have to do open close parentheses. I won't explain why. And then I'm going to square that. So I'm going to do a caret 2. Okay, 4 times pi squared divided by 0.395. And this should be my elastic constant of our inertial balance. And 99.9, which is really good because the elastic constant of our spring is actually 100 newtons per meter is the units for that. Okay, if I put 100 newtons on the spring, it would actually stretch it a meter if it could do that. So there's our k value. Okay, hopefully you figured that out. You're going to have to do that on the Jedi trial. I'll remind you of what the physics equation is. T equals 2 pi times the square root of m over k. And I will tell you, I will give you this equation on the Jedi trial. I'll also give you some equation like this that we got from the experiment. And what you need to do to figure out the k values, you have to set this constant. You have to, first of all, you have to convert this to this equation so that it matches this equation. And then you'll take this constant and it'll equal 4 pi squared over k. And you can solve for k and figure out the k value of any inertial balance that I give you on the Jedi trial. Okay. What's part 4 say? Part 4 says a seconds pendulum. Okay, this is going to introduce you to what we call a seconds pendulum. A seconds pendulum is any kind of pendulum. It takes 1 second to swing one way and back. Okay, so if it's 1 second to swing one way and another second to swing back, that means the period's what? That means the period is 2 seconds, because the period is how long it takes to swing over and back. So the period would be 2 seconds. That's why it's called a seconds pendulum. That means the period is going to be 2 seconds. What is the elasticity constant, K, if you put a 1 kilogram mass on a seconds pendulum? So this isn't related to our pendulum. This is saying solve this equation for K. Solve this for K if you're going to use a 1 kilogram mass and it's a seconds pendulum. All right, so let's do that. So let's go to the iPad real quick. So if we have T equals 2 pi times the square root of m over k, and we need to solve this for k. So you square both sides, you get t squared equals 4 pi squared m over k. And then you take the k to the left side, and you take the t squared underneath. You'd have 4 pi squared m over t squared. Okay, so I'm going to solve for this. What do? Well, the m was 1 kilogram. So on the top, you have 4 pi squared. And on the bottom, you have t squared. What was the period of a seconds pendulum? It's 2 seconds. So what's 2 squared? It's 4. And the 4's cancel out. And the k value then is going to be pi squared. Pi squared. So we'll let Google do that. So I'm going to do equals pi, open, close parenthesis, and I'm going to square it. Okay? And you get like 9.89. Okay? Which is interesting. It's really kind of close to gravity. Gravity is really close to pi squared. It's an unusual thing that gravity on Earth is close to pi squared. Okay, so that's how you find the k value, you solving that equation. All right, the last one is not related to the inertial balance. It's trying to understand how we use graphing to find the linear relationship between two variables. So in this last trial, it says gravity is measured at various locations from the center of Earth, as seen from the table on your Google Sheet. Using this spreadsheet, graph this data and then determine the mathematical physics equation that relates these two variables. Keep manipulating the data and regraphing until you have an r-squared value of 1. So this is what we do in physics. We graph two variables. We try to figure out what's the mathematical relationship between them. How are they related? Are they related just linearly, or is it something a little more complicated? So distance from the center of the Earth was in kilometers, and that is our dependent variable. It's our independent variable. Sorry, it's our independent variable. We keep moving further and further from the center of the Earth, and we want to see how gravity depends on that location. So gravity is our dependent variable. It should be on our y-axis. The distance should be on our x-axis. So I have this one first and this one second. You'll see I have them spread apart, and the reason for that is because we're going to have to do some manipulating as we go through. The first thing we want to actually do is we want to MKS this, and so we want to put the distance actually in meters. We don't want it in kilometers. We want it in meters. So the way to do that is equals. We can take this, and we can multiply by 1,000. I'll put it in the meters. And you can just do that and drag that down. Okay, so we're going to see how gravity depends on the distance from the center of the Earth in meters. So we're going to simply highlight this, and then you can hold down the I think it's the command button. If you're on Windows, it's going to be the control button, but I'm going to hold down the command button and highlight that also. That's going to graph this versus this. Gravity is going to be on my y, distance is going to be on my x. And so I'm going to graph that. I'm going to insert a chart. And here's what I got. Gravity versus distance. Now, this is one of your 7 charts you need to memorize too. What kind of a graph is this? This is an inverse graph. This is an inverse graph. So it looks like as you get further and further away with the distance, go further and further away, gravity goes down. Okay? So what's this look like? Okay, this looks like gravity or distance is proportional to 1 over gravity, or gravity is proportional to 1 over distance. Either way, you could write it either way. Okay, so remember distance was on our x, so this would be like x is proportional to 1 over y, or you could do y is proportional to 1 over x. Either way is going to be fine. So we're going to actually change the x value, the distance value. We're going to regraph this because we're trying to make it a linear line. We want to know what's the linear relationship between distance and gravity. That's the important thing because that's what your equation is going to look like. What is the linear relationship between distance and gravity? We've just proven that distance and gravity is inversely related, we think, because that's what the graph looks like. So what now we're going to do is we're going to graph gravity, not versus distance. We're going to graph gravity versus 1 over distance. So in this next column, we're going to do 1 over d. And I can just have Google do that. I'll do equals, and then I'll do 1 divided by, and then I'll click the distance and hit return. And then I'm going to take that and I'm going to drag that down. Okay, so now what we want to do is we want to graph the 1 over d versus gravity. So we're going to try to grab this, and then we're going to command, and we're going to hold down this. We're going to insert a chart, and it's going to try to figure out what we want. It's going to be really messed up here. So let's do a line graph, but this is not right also. Yours might come out right, but this is not coming out right. So what do we got here? We have no x-axis here at all. So that's weird. So let's do, click on the x-axis, click on this chart here, and we want, go and highlight this. Okay, click OK. And then for the series, click on there, click on the chart, and highlight this. Click OK. There we go. Now we have it. Okay, so here is, and let's go to customize, chart axis titles, chart title. This is gravity versus 1 over distance. Okay. Okay, we'll leave it like that. All right, now you'll notice still not a straight line, right? Actually, let's test to see if that's how straight that line actually is. So if you come back into customize and you go to series, and then we go to trend line, and then we'll do an r² value, 0.991. See, it's completely off the line. It's curving up like this. Okay, and what is that? What is that? Well, that is that's a y equals square y equals x squared, right? As your x goes over, or your y squared equals x, either one, okay? Where it goes up like this, okay? So what we want to do is we want to actually square the x-axis again and see if we can get that to be even more linear, okay? So we did y versus gravity versus distance, which is your y versus your x, and we saw it was an inverse relationship. So we did gravity versus 1 over distance to see if that was going to make it linear, and it's not quite linear again. Okay, so now we have a y equals x squared graph, and so now what we're going to do is so that's what we think the relationship is. So now we're going to do gravity versus 1 over x squared, or 1 over x, the whole thing squared. Okay, so we can see if we can now straighten that out even more. Okay, so we got that one now, And now, so we're going to come up here again, and in here we're going to do 1 over d squared. And we can do equals, and I can do 1 divided by this thing here squared, or I can just do equals this thing squared, which would be the same thing, right? And set 0. And we'll go down like this, and they say 0 because if I need more decimals on there, so I believe, there we go, there they are, okay? All right, really what I need to do is, I wonder if I can do this. Let's do format number, let's do scientific, there we go. So now they're really small numbers now. Okay, so now what I want to do is I want to graph this distance versus this gravity. So I just highlight both those columns, insert a chart. We want setup. We want a line chart. We'll go there. And of course, this is messed up again still. So what do we want for our x-axis? We want, for our x-axis, we want this. Okay. And then for our series, we can edit one of these. Well, let's just remove one of those. And yeah, this one's right. F36 to F42. That's good. That's what we wanted. So what do we got? What does it look like? Look at that. Looks pretty straight. Let's check it. Series, trend line, r squared value, and it's 1. R squared value is 1. So now we know the relationship between gravity and distance is an inverse square law. Gravity is proportional to 1 over the square root, or 1 over the square of the distance. Let's do a series and chart title, gravity versus 1 over distance squared. Okay, do that. Let's come down to series, and let's go ahead and put a series. Since now we have a linear relationship, gravity is linearly related to 1 over the square of the distance. We can actually put an equation on there, and we get this really big slope x plus this small y-intercept. And we're not going to do anything with that equation, but we could do something with that equation some other time. So, okay, so there's my third graph. You needed those 3 graphs on there. Okay, and I'm sure that this was complicated every single year. It seems really complicated, but this is setting up the year, what we do. We take an inquiry. We have a variable that we change. That's called the independent variable. And we see how that affects some other variable. There could be a whole bunch of variables where all the rest of them we're going to keep constant. We change one variable, we see how it changes the other, and we just throw them on a graph. And we look at the graph, and we try to interpret the graph. And if it's already looks like it's a straight line, if we do an r squared through it and it's like close to 1, then we're good. We know what the relationship is, and we can write down the linear equation. But if it's not linear, like if it's an inverse graph, or it's a x squared graph, or a square root x graph, we want to regraph that relationship. We want to do that function. So on this one, we squared the period, and then we regraphed mass versus the period squared. And if it truly was our correct interpretation, now it will actually be linear. When you graph mass versus period squared, you actually have a linear relationship. So that's what we did with gravity. We graphed gravity versus displacement, and we got something that looks like this. And we thought, hey, that looks like an inverse graph. So let's regraph gravity versus an inverse displacement. Let's see what that does. Did that make it a straight line? And no, it actually did it more like this. But we're still going in the right direction now. So we thought, well, that looks like a y versus 1 over a y versus x squared graph. So we did gravity versus 1 over d squared, and we got a straight line. Got a linear relationship with an r squared of 1. So that's what we do in physics. We are trying to validate equations. So we graph it until we get the linear relationship, and then we can prove that with our physics equation. So that's a really big inquiry for the beginning of the year. That's probably one of the toughest inquiries we do all year. And there's a lot of knowledge and information that you can get from this, so you can watch it as many times as you need. So hopefully that helps you, and you can print this all off and insert it onto that page for the inertial balance inquiry.